Okay, and the last talk before the coffee break will be given by Sylvain Marsat from Laboratoire des Deux Infinis at Toulouse about the waveform systematics and sky localization for LISA signals of massive black hole binaries.
Thank you. So it's a pleasure to be here. And yeah, I would like to talk about massive black hole sources for LISA, the sky localization of systematics. So, okay, is it better? Okay, sorry. And this is the outline of my talk. So I'm going to talk a little bit about sky localization qualitatively, what determines how well we localize the signal in main mode, possible degeneracies in the sky, what this means in terms of galaxy counts, and I'm also going to talk a little bit about pre-merger sky localization, and then at the end I will arrive at the subject of waveform systematics for LISA. So first, massive black holes are a cardinal source for LISA. They're very important in the science case. I'm going to go very fast here. The question we want to address is how well we can localize them, which is crucial to extract electromagnetic counterparts. And also how well in advance can we do something? Can we provide an advanced localization, advanced alerts, which is relatively easy, but advanced localization as well. But then there is also the fact that the EM counterpart that we can hope to get are going to come from the golden event, the loudest ones, the most favorable case. And the louder the event, the more the details in the waveform matter, and the more you can bias your analysis if you have errors in the waveforms. That's why the question of error systematics is also very important for this science case. So massive black hole mergers are fairly loud. They can be merger dominated. They can have a strong merger at high masses with a lot of contribution for higher harmonics. And here I have examples of signals. Something that I like to stress is that these tracks that you may have seen in the science case for LISA span quite a few orders of magnitude, right? So qualitatively, the signals look fairly different. At low masses here, you are 10 to the 5 solar masses, you have a signal that is, so this is whitened signal, sorry. So this is basically divided by the instrumental sensitivity. And you can see it's a long in spiral. So it's fairly in spiral dominated signal with different harmonics and colors. At high masses, you have something that is fairly short, completely measure dominated, and with a beautiful ring down at the end. Okay. Now, a few qualitative things about the LISA response. So LISA is different from simply flying LIGO in space. There are some differences here. If you take into account the full LISA response, you have expressions like this for the one-arm observables. Then there are additional complications that we have to build TDI combinations to get to observables that suppress lights and noises, but qualitatively, this is not super important. You can look at just the response of the gravitational wave on one arm and understand what happens qualitatively. So you have effects that are time and frequency dependent. Time because everything is moving, so LISA is moving on its orbit, and frequency dependent because at high frequencies you start to be able to fit one wavelength in one arm, so you start, in other words, to be sensitive to the delay in terms of arrival between the three spacecraft as well, right? But then if you ignore these effects, you come back to something that is a LIGO-like response. And here you actually have information in the different harmonics. So this is a simple response where you just multiply by some constant dependent geometry. But because you observe strong harmonics and multiple harmonics, you actually have information here as well. So on the right, you have an illustration where you can see, so the constant would be this simplified response. At the low frequencies, early times, you have actually the effect of the LISA motion that creates all these modulations. And at the high frequencies, you have the effect of departure from long wavelength approximation. So you start to be sensitive to the delays between the spacecraft. If you look at the structure of this response, you find that you can have degeneracies in the sky of LISA especially for the signals that are short transients. So these loud mergers that are short transients. So this is a plane of LISA, and you can have up to 8 modes in the sky that you can recover. And the most common that you're going to have is you're going to have unimodal, bimodal, or up to 8 modes. So the bimodal degeneracy is the most common, is a reflected sky position. So reflected with respect to the sky, to the true position, reflected with respect to the plane of LISA, sorry. But then if you look at the response, you can see that you have degeneracy breaking. So the motion of LISA itself eliminates some of the modes early on, except the antipodal. And the high frequency effect in the response are actually fairly important because they eliminate all of them except for the reflected one. So you have an illustration on the right of how this happens as you increase frequency, as you accumulate data. So you have degeneracy broken, but those effects are also not very strong in the response, actually. They're subdominant. Now, let's look a little bit at the scale localization and what you get. So I'm going to first ignore degeneracies for now, and just focus at, okay, we have a main mode in the sky, assume it is Gaussian shape, what determines the size of the errors that you have with LISA. And this is done with a superficial matrix computation. So there is quite a bit of information in this plot. What you would get baseline, if you consider the full response, is a blue line. So it has this shape. This representing redshifted mass, and is keeping just the redshift fixed. So this is what you would get at redshift 1. And the range corresponds to the 90% range that you would get, randomizing over everything, orientations, mass ratios, spin, etc. Okay. So you can see that we have a very good localization in the sweet spot of LISA sensitivity, particularly at higher masses, where the median here goes below 1 square degree. You can see something very important is that you have a huge dispersion, right? You have 4 orders of magnitude of dispersion in sky area. So if you ask someone what is scale localization with LISA, you have to actually specify which signal you have. This is good news and bad news. It means that even in the sweet spot, you have signals that you cannot localize very much, but it also means that you have fair amount of golden events that for which you're just lucky, and where you would get fairly good localization here. So if you care about the best of the best, it's actually good news. One thing that we do also here is the different color curves corresponds to turning on and off the different effects I was talking about. And you can see that the simplified response, where you ignore everything, actually kind of drives, is actually almost correct for the high masses already. So it means that you have a lot of information that comes from this pattern response, just the response for different harmonics, right? And the effect that, most important effect is at low masses, then you can see that freezing the LISA motion is wrong. So it means that you have an information coming up from the LISA motion. At low masses, the signal is longer, so you see more of the LISA orbit. So that makes sense. Okay. But this is important for. I spent quite a lot of time here because it's important for systematics. So the pattern function response is the main source of information here. And the multimodality is broken by the, as we said, is broken by the other effect, but it's not what brings you the most information about the size of the main mode. And this is important because this is different from LVK localization, where you have, say, physics-independent information. In LVK, you have time of arrival, you have triangulation, right? So, and this doesn't really depend on how good your waveform is, right? Because it doesn't really depend on the, it's pure geometry, doesn't really depend on the waveform. But the information that we get here depends on getting accurately the different waveform pieces and the different harmonics. And if we have slightly inaccurate here, we can actually have problems in our modeling. Okay. This is just an illustration translation of what I was showing before. It was a fixed redshift 1, just to put it in the source frame and redshift space. And the 2 lines correspond to 0.4 that was taken for original antenna design, and 10 square degrees, which is LCC field of view. And you can see the kind of contours we get for the median sky localization in this space. So we have a fair amount of parameter space where you can, or we can localize in principle to sub-square degrees. And of course, if you consider that you're very, very lucky and you consider the very best of the systems, you can do significantly better than this. Okay. So don't just stop and look only at the median. Now, what drives these 4 orders of magnitude of dispersion? We try to look at what are the most important parameters. And we found that the most important ones are the inclination and the latitude. So in this LISA frame, okay. So this is just contour plots in inclination and latitude in the LISA frame for both the SNR and the sky localization. So this is a 90% sky localization in square degrees. And you can see the trend that you expect is that if you are edge on, so close to inclination is pi/2, it's not very favorable in SNR, that's the lowest SNR region. And indeed, you do not get a very good localization here, but you have another trend that goes against this now. In the latitude, that is better to be, it's better if the source is in the plane of LISA, actually. And this goes against what you would expect in terms of the SNR. Those are low SNR, relatively speaking, sources, but those are really the best localized ones. And there is quite a bit of difference between the favorable and unfavorable regions, right? Now, what I presented before was just the Fisher matrix already. Oh, okay. Fisher matrix analysis. So we tried to look at full parameter estimation, to look at sky multimodality. So this is just considering different population models, putting them in the parameter space, doing Bayesian analysis and looking at the relative weights between these 8 modes. And in blue, what we find is a signal that are unimodal. In red is the one that we have this bimodality, and in yellow, there are either 8 modes or very badly localized in this region. So you can see that it can happen. There is quite a bit of randomness, but the multimodality will mostly happen at high redshift, not surprisingly, and also at high masses. We can have multiple modes here, because those are completely low frequency signals and completely major dominated. This is a translation of what I was showing before for galaxy counts. So it's not sky localization only, but it's volume. So the error in luminosity distance behaves a little bit like error in sky, as I was showing above. But we also have to consider, for looking for counterparts, we also have to consider the mapping between luminosity distance that is observed and redshift. And here, lensing errors, weak lensing errors matter, and they kind of dominate. So the error of LISA in the sweet spot is better than 1%, and this is actually dominated by the lensing error beyond redshift 1. Okay. It's important to take that into account. And those are simply cumulative distributions for the population catalog that I was talking about before, for 4 years of observations. So this is a distribution for sky areas. And if you consider the volume, if you consider a simplistic model for the density counts of galaxies in the observable universe, you arrive at this kind of distribution of counts, right? So the black line is 1. And you can see that in the free models, population models, you never have in 4 years more than 1 expected uniquely determined source just for gravitational observations, looking at galaxies in the box and finding only 1. I should say these are galaxies that are, I put some mass threshold here, right? Again, that's a gross simplification, putting some mass threshold, assuming that only the massive enough galaxies can be considered as probable hosts, okay? But you can see that you can have, if you consider 10 or 100 galaxies in the box, depending on the scenario, you can have a few or 10 sources that will be in that regime, right? So 10 to 100 galaxies in the error box, and the question is, what can you do with this kind of information? That is more for astronomers to answer. Premature sky localization. In short, fairly difficult because a lot of information comes from the major. So those are simply tracks of the x-axis is time, and this is a refinement of sky localization as a function of time. And at the end, you have a jump when you have the other information coming from the major. And those are 3 masses. At the top, you have redshift 1. At the bottom, you have very optimistic redshift of 0.3. And you can see that the premature localization for the massive systems is fairly difficult. It's very hard to get to useful field of view before major. At low masses, it is best case because the signal is much longer, very in spiral dominated. And you can get to interesting sky localization, especially if you consider the optimistic redshift, quite a lot in advance. Then it's relatively flat, right? So you get to sub 10 square degrees fairly early on, like a week or even a month before the major. Multimodality is more important in premature sky localization. What I've shown before was just one in the sky. But again, for the massive system, you get a lot of multimodality before major. This increases the difficulty of doing anything with premajor for massive systems. Now, waveform systematics at last, in the last minute. So the idea is that you have an error between the true signal from general relativity, and the models that are covered by your waveform templates, waveform model. So you have a bias corresponding to the shift between the best fit waveform and the truth. And as you increase the SNR from green to yellow to blue, sorry, you increase the SNR from blue to yellow to green, you have a better statistical error shrink. At some point, the bias becomes statistically significant, right? So I'm not going to detail the settings. We just did a large number of PD runs to see what could happen, injecting and recovering with different waveform models. And this is kind of situation that we got. So in all this analysis, we find it's fairly difficult to do this bias analysis. So we start from artificially high redshift, low SNRs, and we lower the redshift progressively and increase the SNR. So you can see at the beginning, you have a very bad scale localization. You increase the SNR, you increase the SNR, and this is a relatively good case where you end up with no significant bias. So your true value is compatible with the posterior that you have in the end. And this is typically what happens at the low masses. You can have other cases. So this is a higher mass system. And you have a situation here where, okay, error shrink, and at some point, you end up confidently wrong. Right? The bias is very statistically significant, and you have a big shift between what your posterior is, where you would point your telescopes, and the truth. And you can also have cases that are a bit weird, where you refine your analysis, and at some point, you switch to the wrong place of the sky in terms of sky degeneracy. And you end up at a place that is shifted from the true position, but also it's one of the wrong modes in the sky degeneracy. This can also happen. These are just histograms giving you a more statistical sense of what I just explained. At low masses, we get reasonably good agreement in this is one of the two directions in the sky. The gray area corresponds to something that is bias is not too significant. And you can see that low masses, it's okay, but as soon as you go to higher masses, major dominated with strong harmonics, you have a lot of significant biases at redshift 1. And we also have a sizable amounts of cases in those two cases where we end up on the wrong mode. All right, and I will leave you here with my conclusion. Thank you.
Thanks a lot, Sylvain. So we have time for a few questions before coffee break.
A very nice talk, and my ignorance here again, but can you use the fact that LISA will move, of course, around the sun to optimize the location? Because I understand that your SNR map and your localization map will change during the rotation around the sun, but I don't know if it can be used to improve everything in the estimate of the position of the future merger.
So the motion is very important, and then it depends a lot on the source, whether it's a loud transient or whether it's a long-lived signal.
Yes,
so,
of course.
Here, the longest lived signals are presented are 10 to the 5 solar masses. They last for a few weeks to a few months.
Yes.
LISA will also observe much longer lived sources, like galactic binaries at the extreme or extreme mass ratios, and those will really last for years. And here you really have the full motion of LISA. You see a full orbit of modulation, and you have a lot of information coming from here directly. For massive black holes, it completely depends on the mass range you're looking at. I think I have actually an illustration. Okay, maybe I will not find it. Yes, this is one. An illustration of how, so this is how long before merger you reach SNR 10 as a function of mass. And you can see that high masses, you're basically limited to just a few days of signal. If you go down to 10 to the 5, you have some signals that are 100 days is 3 months. And here the motion actually helps you. We include this in our analysis. It's very useful information where you can have it.
Okay, thanks. So there seems to be a question on Zoom.
Hello. Hi, Sylvain. Excellent talk, as usual. I have a question on this slide where you showed the number of galaxies in the box. So there you took a galaxy mass larger than 10 to the 10, but for LISA sources, and for black holes of mass 10 to the 6, I can easily expect stellar masses of 10 to the 8, 10 to the 9. How much do the numbers increase if we decrease the galaxy mass to, say, 10 to the 8?
Right. So I try to say this is very simplistic. Okay, so don't open me too much. But yeah, I expect basically an order of magnitude degradation increase in these counts if you decrease the threshold to 10 to the 9, and maybe another order of magnitude if you decrease to 10 to the 8. Right. So yes, I mean, I don't know what is a reasonable threshold to pick here. And of course, yeah, if you're in a situation where you have multiple galaxies here, you don't want to depend too much on your assumptions, but maybe if you want to do any follow-up analysis, at least having of the order of less than 100 massive galaxies in the box is somewhere to start. Yeah.
Thank you.
Thank you. So we have time for a question.
Thanks for the nice talk. I'm sure I have a naive question because that's not what I do, but are the biases due to the fact that the sampler is not sampling the multimodal likelihood properly?
So the biases I was talking about were due to mismodeling of the waveform models themselves, right? So Laura talked on the first day about the various methods that you have to try to approach GR waveforms. And it's always going to come with some errors. So the sampling itself, so sampling a multimodal posterior is a little bit of a challenge, but in principle, if you run your sampler for long enough, it's supposed to go there, right?
Well,
So
it depends, really. So have you actually looked at the likelihood?
Yes, I mean.
Over the whole volume. So you see that it actually, the maximum is at the wrong place.
So it's nearly impossible to be completely confident, but this is a procedure that I found works quite well. If you start at artificially low SNR, so you start by exploring the whole parameter space by putting yourself at SNR 20 or so, and only then do you refine step by step to go to, refine your analysis and go to tighter and tighter posterior. And each of these steps is also using parallel tempering MCMC. So you have, every time when you sample this posterior at a given SNR, you're also exploring tempered likelihoods as well. So you have some chains that explore around. Even with all that, it's actually pretty challenging to be sure that you always have the right bias. You always have the possibility of ending in the wrong force maximum in your posterior.
So you haven't actually checked like a matched filter, one template at the, closest metric template value. So not just the likelihood there computed, just to then compare it with where it converges and understand whether it's a problem of the sampler or a problem of the, for example, waveforms.
I mean, this is done implicitly when the sampler evolves.
Well, if the sampler travels there,
yes,
which you can be 100% sure of. So that was my question, really. How sure are you that you sample the metric closest point so that you really know what the reason of the bias is?
Okay, my answer would be fairly confident because it took quite a lot of effort to make sure that this would work, but you can never be 100%.
Unless you actually do the one evaluation of the likelihood there, and then you know for sure.
But you don't know where to go.
You do, because you have a metric. So you know what the metric closest template would be. And that's the place where you expect the maximum of the likelihood.
But I mean, in the presence of a bias, you don't know in advance so you don't know in advance what is the max likelihood location, because you have the difference between the model waveform and the truth. So you have a shift and you have to explore for it. And this is a multidimensional optimization problem. In our case, it's an 11-dimensional optimization problem. And the stochastic method like MCMC is the only way to actually explore this.
Okay.
Maybe we can talk.
Yeah, okay. Thank you very much.
So thank you, Sylvain. Let's thank all the speakers this morning.